Now we'll take a quiz based on the notes that we ran through, which you can find in your Edmodo folder called Work, Power, and Energy, and the practice problems we did concerning the work-energy theorem. This video is a quick overview. The definition for work coincides with the formula for work. It is the amount of force exerted over a displacement. In order for work to be accomplished, this force and the displacement have to be in the same plane, or parallel. Examples would include pushing on a box horizontally that slides horizontally. The unit is a combination of the units for force, the Newton, and the unit for displacement, meters. The unit for work is the Newton meter, which we rename the joule, symbolized with a capital J. Here's a sample problem. If the force applied is 1,000 newtons and the displacement is 0.8 meters, to find the amount of work done, we would multiply the force of 1,000 newtons times the displacement of 0.8 meters for a final answer of 800 newton meters, or 800 joules. Positive work is done when the direction of the force and the direction of the motion are the same, meaning they are parallel and in the same direction. Negative work is done when the force and the displacement are in opposite directions. However, they are still parallel. If the force and the displacement are perpendicular to one another, there is no work done. An example of this would be lifting a heavy box, but walking horizontally with it. The force is vertical, but the displacement is horizontal. There is no work done. Likewise, if there is no displacement, there is no work. So pushing on something that does not move results in no work. Here's a demonstration. The little dude here can push on this wall all he likes and exert more and more force. However, if the wall never moves, no work is done. Work can only be done if the displacement is not zero. Likewise, work cannot be done if the force is zero. If little dude is just standing there not exerting a force, no work is being done. This is the complaint of many employers. Now here we have little dude pulling a wagon. The displacement is undoubtedly horizontal. In order for there to be work done, the force would also have to be horizontal. This is where our mad math skills come in hand. Since the force is being applied to the handle at the angle, we know that it can be resolved into horizontal and vertical components. So if we take the horizontal component of that force, that is the one that's in the same direction as the displacement, and work can be calculated with the f of x times the displacement. Now let's talk about the relationship from this equation. In order for the same amount of work to be done, if there's a change in force, there would have to be an opposite change in displacement. This is an indirect relationship. The point of the relationship is that in order for this equation to remain equal, there would have to be proportionally opposite changes in force and displacement. Otherwise, it's no longer equal to the same amount of work. However, if either the force or the displacement is increased, then the amount of work done does increase. We refer to that as a direct relationship. The increase in either force or displacement is proportional to the increase in work. If both force and displacement increase, the amount of work increases proportionally. For example, if we double the force and double the displacement, then the change in the total amount of work done would be an increase of 4. The relationships all go back to the equation. While there's more than one type of energy, at this point we're concentrating only on the kinetic energy, the energy due to motion. if there is no motion, or if velocity is zero, then there's no kinetic energy. The formula is 1/2 times the mass times velocity squared. Only velocity is squared. Here's a sample problem for kinetic energy. The mass has to be expressed in kilograms. Velocity is expressed in meters per second squared. When we substitute this into the equation of kinetic energy equals 1/2 times the mass times velocity squared, our units in the end work out to be kilogram meter squared per second squared, or in other words, a Newton meter, which is also termed a joule. Notice that the unit for kinetic energy is the same as the unit was for work. Now let's talk about the relationships found within the equation for kinetic energy. As with all equations, when we have two expressions multiplied on the same side of the equation, they have an inverse relationship. But because this equation is mass times velocity squared, that doubles that relationship. So a change in velocity would have to correspond with twice the change in mass in order for kinetic energy to remain the same. Likewise, there is a direct relationship between the kinetic energy and a change made to either mass or velocity. But if a change is made to velocity, remember that's squared, so that would really increase the kinetic energy. Always refer to the equations when answering questions about the relationships. We can combine the equations for work and energy. They are equivalent. Therefore, force times displacement is equal to 1/2 mv squared, the kinetic energy, if we consider that the potential energy at that point is zero. When we did the notes, we calculated this example to show that with the two equations and the data given, the answers are the same and with the same units. Therefore, we can set these equal to each other. Let's look at another sample. If we set these equations equal to each other, work being force times displacement, and kinetic energy being 1/2 times the mass times the velocity squared, as long as we're given at least 3 pieces of data, we can mathematically solve for the fourth. Let's consider this example. A 3-kilogram box is pushed with 400 newtons of force for 2 meters. What is the velocity of the box? As always, we want to solve this using the guess method. Let's identify our given information. We're given the mass, force, and displacement, and we're asked to solve for the velocity. So let's substitute this into the equation and solve. So mathematically, we'll be multiplying 400 times 2, and then we will take the 1/2 and the 3 kilograms and divide it to the other side of the equation so that it's equal to v squared. Then we will take the square root to solve for v. So that our final answer is 23 meters per second. The units work out as well. Within a Newton, kilogram meter per second, we cancel out kilogram that we had divided from the other side. So now we have meters times meters divided by seconds squared. If I take the square root of that, it becomes meters per second, which is appropriate for velocity. This is an example of using the work-energy theorem. In conclusion, if more work is done, then greater energy is exerted. Now all you have to do is review the notes and review the work that you've already completed, and you'll be ready for this quiz. Good luck.